and conditions regarding this webinar or a presentation. And throughout this presentation, your microphones will be muted and your videos will be switched off. This is to make sure no interruption to our speaker. And at the end, after the presentation, you will be given 10 minutes for question and answer sessions. So during that session, you can ask questions. And also remember, throughout the presentation, if you do have any questions, you can post them in the chat box so we can entertain them at the end. And so without further delay, and also I would like to mention about the SLAAS. So Sri Lanka Association for the Advancement of Science, or SLAAS, it's a premier organization of science in Sri Lanka. And the theme of the SLAAS for this year is the science and technology for better tomorrow. I think your presentation is ideal for our theme, because today in this presentation, synthesis of highly controlled, functionalized, biodegradable copolymers as a solution for the ever-growing plastic waste problem will be introduced. In addition, generation of high-value biodegradable materials to be used in medical and electronic applications will also be reviewed. So it's without further delay, it's my pleasure to introduce our speaker today, Professor Parisa Mehrkhodavandi, and she has completed her PhD with Richard Schrock at the Massachusetts Institute of Technology. And she went on to do a postdoctoral research at the California Institute of Technology, working with John Bercow and Richard Grubbs. And it's a pleasure and it's honor to mention her both supervisor Richard Schrock and her postdoctoral supervisor Professor Richard Grubbs. Both were the Nobel Prize winners for 2005 chemistry, and it's honor to have you, Professor Parisa, with us today. And also continue the Professor Parisa Mehrkhodavandi. She is now. She has started an independent career at the University of British Columbia in 2005, and she has been there as the pioneer in using the main group element indium as a catalyst in ring opening polymerization reactions. To this end, her group has published multiple studies on the structure-function relationships of indium and other group 13 complex in catalysis. She also holds patents on several catalysts developed in the course of this research. Professor Mehrkhodavandi has won multiple awards, including the University of British Columbia Killam Research Fellowship and Alexander von Humboldt Fellowship. Her current research focuses on catalyst development and the synthesis and characterization of new families of bio-based, biodegradable green polymers. So it's a pleasure and honor to have you with us, Professor Mehrkhodavandi. So the Zoom platform is over to you. Thank you very much.
Oh, thank you very much, Professor De Silva. It's such a pleasure. I have to say that there are very few things about this horrible pandemic that I can say are amazing, and this is an amazing opportunity. It's such a pleasure to have one of my wonderful current graduate students, Chiral, introduce us, because it really opens up for me a chance to see you at least in silico. And I'm drinking some tea from Sri Lanka.
Okay.
To kind of feel that I feel that I'm there with you, at least in some parts, because the tea comes here. So thank you very much for the invitation and the wonderful introduction. I'm going to share my screen. Hopefully everybody can see this. Is that okay? Can you see
Yeah,
the screen?
we can
Okay.
see. We can see the screen.
Fantastic. Great. Thank you very much. So I want to tell you a little bit about some of the work that we've been doing in my group in the past few years. And what I will try to do is give you a bit of an overview of some of the things that we have been able to do with using indium as a catalyst in ring opening polymerizations. So we're interested in biodegradable polymers, and the question becomes, what are some of the reasons why we're interested in these materials? One of the first things to think about, and one of the first things that people think about, is waste management. So the issue of plastic waste in our environment, which is a problem worldwide. Everybody has been dealing with them. I have very specific thoughts about this issue, but the kind of research that I started off doing was to try to develop a catalyst system for making, you know, a lot of single-use plastics biodegradable. And there's still a reason to do this research, but in the past 15 years, I've really changed my mind about what we need to use plastics for. So plastics are indisposable. They're for certain applications, as we have seen during this pandemic, there are certain applications for which we, at this point in time, cannot replace plastics. And so the idea becomes there's certain applications where we should not be using plastics, and other applications where we should be replacing the plastics that we have currently with biodegradable material. And then this moves us to a whole other area where there are high value applications where the biodegradation is actually a feature of the polymer. So for example, I've shown you in the case of biomaterials, where if you have, if you're trying to use biomaterials in the body, for example, as a temporary stint, you actually want that plastic to degrade because it's necessary for it to do so. It prevents further follow-up surgeries, etc. Also, in drug delivery, these are applications where having specific synthesized, biodegradable, and bioavailable material can be really, really helpful. So why India? So if I'm interested in developing functionalized polymers, high value polymers with functional groups, we chose from the very beginning to use indium. It's kind of a random metal to think about in the beginning, but where indium is used quite significantly in industry is, of course, in the indium tin oxides and the use of displays, etc. And if you have heard about indium scarcity, this is a question that a lot of people ask. Is indium scarce? Well, if indium tin oxide is going to be used in every single display on Earth, this will become a problem. So as a bulk material, as an element used in the bulk material, it actually can become scarce. Indium is generated as a byproduct of zinc mining. And so if we're going to use up all of our indium in indium tin oxide displays, it can become a problem. In a catalytic sense, in the way that I'm interested in using indium, it actually is far more abundant than all of the coinage metals, rhodium, ruthenium, gold, silver, etc. And I've been working actually with the premier producer of indium in the world, the Indium Corporation, to look at possible applications of indium in catalysis, and I'll tell you why that is. But the other question that I get about indium is it toxic? And the toxicity of heavier main group elements is entirely dependent on their oxidation state. So indium generally is found in the trivalent oxidation state, and in that state, it's used as a indium oxide pills that you can take or drops that you can take. And I'm not suggesting this, but this is what the marketing for this material is. This one material, this company says you can live without indium, but you may not achieve optimum longevity without it. So I keep you forewarned that you should be taking your daily dose of indium according to this company. please don't. But just in terms of toxicity, indium-3 is taken internally and is not toxic. Okay, so when we first started this journey into indium chemistry, there was exactly one compound by Wang and co-workers for the ring opening polymerization of cyclic esters. Organic chemists had been using indium-3 for a very long time in a lot of different applications as catalyst, as a Lewis acid, etc. But in terms of well-defined indium compounds that were used in catalysis, and specifically in polymerization catalysis, there was exactly one. We reported our first example of the system in 2008, and since then, there have been a lot of different systems. They don't fit on a page anymore, and I've stopped adding to the slide. The slide stopped getting updated a few years ago. So what I think we showed was that we can use indium in catalysis in a really effective way, because indium being a lower, a group 5, or sorry, 5th row, group 13 element, is very resistant to degradation with water and oxygen. I'll show you an example of that. And that had made it a really good Lewis acid to use in a lot of organic transformations. And people have showed later that even when you take that indium, you put it in the right ligand framework, you can actually do some beautiful chemistry with indium if you can control certain aspects of aggregation, etc., in the system. So I'm interested in ring opening polymerization in particular, where you take a strained ring. So in this case, I'm showing you a lactone here and a specific lactone, which is a lactide, and we're carrying out ring opening polymerization, ROP, to generate a polyester. And we have looked at a lot of different aspects of this reaction and this catalysis with indium chemistry. I'm really going to just give you a highlight here and then give you little tastes. So we started off with these dinuclear indium complexes, and this motif comes up again and again, where indium, because of its larger ionic radius and because of its Lewis acidity, actually tends to aggregate. And one of the keys to understanding and controlling indium reactivity is controlling this aggregation. We have then worked on really looking at developing chiral analogs of this work. And this is work that was initiated and really worked on by a Sri Lankan student of mine, Dinesh Aluke. And Dinesh really expanded this. I'll try to touch up on some aspects of it. We then used some of our catalysts to really do chemistry that wasn't really possible prior to that, which is highly controlled block polymerization and formation of more complex polymer architectures. And finally, and what we're really into recently is cationic indium compounds, exploring their reactivity and exploring their catalysis or their catalytic activity. So I'm going to talk about, so of all the things that we're working on, today I'm going to give you this idea. I'm going to tell you a little bit about this project. So taking cyclic esters and ring opening them in a controlled fashion to make block copolymers. I'm going to talk about taking those cyclic esters, like lactide, for example, and making copolymers with epoxides and cyclic ethers, or making copolymers with acrylates. So in this case, methacrylate. And then finally, I'm going to show you a way to effectively block copolymerize epoxides and lactones by going through the spiral orthoester intermediates. And if you choose the right catalyst system, we can form these 100% in situ and then ring open them effectively, forming an alternating copolymer with epoxides and lactide. So let's start with the first story. This is the first thing that we started working on in my group. And when we developed these indium compounds, we started looking at ring opening polymerization, and we determined that they are incredibly controlled for the ring opening polymerization of lactide. So this is a reaction where we can take up to 2,000 equivalents of lactide. This has actually gone up to 20,000 equivalents of lactide, and we can predict the molecular weight of the polymer that we get. So the line here is the predicted molecular weight. It's not a line through. This is actually what you would predict. And the blue are actually the polymers that we're getting. So what we're getting are polymers where we have really slowed down or basically stopped any chain end, the chain termination reactions. We can do this with a variety of different cyclic esters. I'm just going to show you two of them here. Butyrolactone is a 4-membered one, and it's generally tougher. And for all of these cyclic esters, what we can do are block copolymerization reactions, where you can add your first equivalent of monomer, and that's the first one here. You can observe that. You can see that it's a beautiful monomodal, very highly controllable polymer. Then we can add another 200 equivalents of monomer and see that this beautiful shift of this polymer to the higher molecular weight that you expect. And you see that when you do lactide or butyrolactone or caprolactone or different cyclic esters, but you also see that when you mix them. So when you start from lactide, you add butyrolactone, you go to lactide, and you see the same behavior, right? Where you start looking at higher and higher molecular weight reactions. And this is also some of the work, early work that Dinesh did in my group. So it's a really highly controlled system. The reason that it's controlled has to do with this asymmetric nature of this alkoxide and the chloride. And we can just swap out this alkoxide with any other alkoxide. So here I have an ethoxy bridged, so 2 indium centers, a chloride bridged, and ethoxide bridged. And you can just add a different alcohol, in this case, this triol, and it's very easily swapped out, and you form ethanol as a byproduct, and you form this compound. You can form it in situ, and this species is what leads to the formation of these beautiful tri-armed polymers. We've worked with a group of Savas-Hatzikiriakos to study these materials, study their copolymers, understand the rheology of the material, ensure that we've had 3 arms, etc. And so that reactivity is possible because of this exchange of an alcohol and this alkoxide. The reason these systems work so well is that there's 2 possible mechanisms for this reaction for lactide polymerization. You have a Lewis acidic metal center, and in both mechanisms, the lactide can coordinate to the Lewis acidic metal. The ketone here gets activated, and then an alkoxide will then, a coordinated alkoxide will then attack this activated carbonyl, leading to a ring opening event. The question that we came across was, we start from a dinuclear indium system. Does it break apart to a mononuclear system, or does it stay as an aggregate? And overwhelming evidence, both experimental and theoretical, has shown that in fact we stay as a dinuclear system. And this is really a feature of indium because of the larger ionic radius. The stability of this dinuclear center allows for the 2 metals to basically protect that chain end, and that protection of the chain end prevents it from going back and carrying out any other side reaction that would prevent chain propagation, and it would lead to chain termination. And so this is the fundamental reason to use indium, this ability to aggregate. And if we can control that aggregation, we can use it to do chemistry that wasn't possible before. So I'm going to condense a decade's worth of work in one slide, where we played around with the ligand framework on the metal, and we really started understanding what these indium systems needed electronically. We started putting them together in a ligand platform. We started looking at chiral systems, and so we finally ended up with this particular system that we published in 2017, which shows the kind of culmination of this chemistry, which is basically that we have an indium compound that's an indium hydroxy with tetradentate ligand around it. And this material is completely air stable. So it's an air stable solid that then in air we can add this alcohol to. And in air, and we're talking about Vancouver air, so Vancouver is quite humid. And under these conditions, we can add unpurified lactide, different enantiomers of unpurified lactide. And what we could see was really beautiful polymerization, forming very well behaved, very well basically the same theoretical and observed molecular rates. And if you compare that to the purified system, you see basically the same thing. So what we were able to do was, because we were using indium, because it's air stable, because it's water stable, we don't have to go through a purification. We can do this reaction in air, which was really cool. And there was no solvent required. So we were quite excited about this reaction. But that's just the kind of the background for the indium chemistry. What I want to focus on is this middle section, which is this copolymerization reactions. And the way that we're looking at these is to really expand the families of catalysts that we're making. So one of the polymers that we really are interested in, or were from the beginning, is a polylactide copolyacrylate. And the reason for that is that polyacrylates are used in medicine quite a lot. Polylactides are degradable, and so could be very useful in medicine, except that they're brittle and they have poor flexibility, and they don't have the physical properties that are necessary to do a lot of the chemistry that we want to be able to do. And if we were able to generate block copolymers of this material, we're hoping to generate amphiphilic polymers that would allow us to start looking at self-assembly and start looking at larger, more organized structures in solution. And that's what you would be able to get if you can get controlled amphiphilic blocks, which we could in this case with acrylates and PLA. So how do you make these? So this is PLA block polymethyl methacrylate in this case. How do these have been made before? They've been made before with a combination of ring opening polymerization and atom transfer radical polymerization, where you can polymerize your lactide and you end up with a hydroxyl chain end, at which point you use an atom ATRP reagent, generate a halide, and then you use a copper catalyst to do methyl methacrylate polymerization. You can combine ROP and ATRP using a bifunctional initiator. You can use combined ring opening polymerization and the raft. So you have to have a bifunctional initiator, and then you can use the reversible addition, fragmentation, chain transfer, radical polymerization. All three of these systems work, but as you can see, they're either multi-step reactions, they require purification at every step, or they require a pre-designed initiator. So this is a non-trivial reaction, right? So you can make them, but it's not trivial. It's a difficult reaction to do. Also, what we want to be able to do is something really simple. To have a catalyst that to do exactly what I showed you in the previous segment. Add one monomer, polymerize it, add the second monomer, and form a block copolymer by simple sequential addition. And before our publications, this was not known. The only example of it, of anything similar, was this organocatalyst system with caprolactone and methyl methacrylate, which generated a random copolymer, which is not something that we need, because we want to have those two blocks to allow us to form the amphiphilic polymer to actually make the micelles and the superstructures. So this is a work by June Jung, who's a current graduate student in my group. And what he did was he first of all looked at the homopolymerization of methyl methacrylate, lactide, and caprolactone with a number of different systems that we had in our group, both neutral. So in this case, these two are neutral indium compounds, indium alkyl compounds, slightly different. One of them has an amine and one of them has an imine linkage. And then cationic analogs where we have amine or imine ligands, and we have different counterions. And what he showed in this paper was that these systems were not actually active for metamethacrylate polymerization, the cationic ones. I'll get back to cationic systems a little bit later. The neutral ones were. So this particular system, system 4, for example, was effective for the polymerization of methyl methacrylate, lactide, and caprolactone. And this is exactly the system that we wanted. So we carried out these polymerizations, and the question becomes, what is the chain end of these systems? Well, the chain end is this alkyl group. So this alkyl group is a nucleophilic initiator for all of these. This is what the polymer looks like. So that's important. The question becomes, are these living systems? They're not living systems. There's a relatively low initiation efficiency. But at this point, I don't actually care if they're perfectly living. I'm trying to make a polymer that nobody's ever made before in this way. So I just want to see if it works. Why do the neutral systems work and the cationic systems do not? The neutral systems, you can see this is using IR spectroscopy. The neutral systems are able to, if you see free methyl methacrylate, polymethyl methacrylate, you can see that the free methyl methacrylate is slowly converting to polymethyl methacrylate after heating. So this goes from here to here. However, when we look at the cationic systems, this doesn't actually happen. So when you go from free methyl methacrylate, instead of going to polymethyl methacrylate, they actually form a new band here. And this is, we believe, due to this cation acrylate interaction, which is basically shutting down the catalyst, which is why the cations don't work. We formed the copolymers, and so now the question isn't just that we've added the two monomers and formed a copolymer. The question is, did we make the copolymer, and what kind of copolymer did we make? So we had to really do our homework in trying to understand whether we were making, in fact, a block copolymer. So the first thing that we looked at was GPC. You can see the molecular weights for the homopolymers are uniformly, under the same conditions, lower than the molecular weights for the block copolymers. But since this is not a living system, as opposed to our beautiful first story where everything was perfectly living, it's not enough. This is not enough to convince us. So then we looked at fractional precipitation, where we're looking at a technique that allows you to look at the amount of solvent that you're adding to precipitate different fragments of the polymer. And what we saw was if we had polymethyl methacrylate, PLA, or PCl, or this value, the Y1 minus Y2, I won't get into this, but it has to do with how much solvent you have to add to precipitate these material, would be the same as these other polymers. And it's actually not, it's an intermediate number. So that's second piece of data. The other one is looking at the glass transition temperature and melting temperature for these polymers. And if you look at the polymers that we're generating, they're somewhat intermediate to what we would expect for PLA, PCl, and polymethyl methacrylate. So that works. And finally, we did in situ Josie NMR spectroscopy, which allows us to look at the diffusion coefficients of these polymers. And what you can see from the peaks, not very clearly, but this you have to take my word for it, is that the PLA and the polymethyl methacrylate in solution are actually diffusing at the same rate, and so they're the same molecule. So when you see the peaks in the NMR spectrum, the DOSI tells you that they're diffusing at the same rate. So this really convinced us, and my student June was really pulling out his hair about this, but it really convinced us that in fact this is a block copolymer, which is really exciting. And what's really exciting about it is that it's actually, formation of this material is completely unrelated to the order of addition. So we can either add the lactide first, and we know that that chain end is that alkyl group. It's a good initiator or good enough initiator. We can form the alkoxide, and then the methyl methacrylate, once it's added, goes through a Michael addition reaction. to give us the block copolymer, or we can go through that alkyl group, the indium TMS methylene group is a good enough initiator to actually to start off the Michael addition reaction. Once you get the first one, everything else goes. And then here you have an alkoxide, which can then carry on an insertion reaction, and you can go ahead and do lactate polymerization. So the initiation efficiency for either of these systems is not good, because that TMS methylene is not a good initiator in either case, but it's just good enough to get both of those reactions to work. And that's the key to this chemistry, I think. So this is really exciting for us, and we are now looking at the applications of these material and looking at the rheology, etc. A little bit hindered by COVID, but hopefully we can go ahead with that. But I sort of vaguely hinted at this. We had used cationic indium complexes. They didn't work in the previous story, and I showed you why they didn't work, because they were coordinating to the accolade. But actually, if you look in the literature, and my student June did, so during the pandemic lockdown last year, he actually wrote a review article on this in this issue, which was that there were 0 reports of cationic indium complexes in polymer synthesis. There just weren't any. And even in catalysis, there are exactly 6 reports in all of organic or inorganic catalysis for cationic indium complexes in catalysis. And it was surprising, because these are 2 here where you see that cationic systems are actually more active than the neutral systems. So we were excited about this. We had shown that, you know, in some cases they don't work, and what we realized is that people don't really know very much about cationic indium complexes, full stop. There just isn't very much information about these systems, and so we were really interested in exploring the chemistry of these cationic indium systems. And Chiral took on this project, and the question that he was interested in is this idea of having a hemi-labile arm. So I showed you that if you have this open coordination spot, if you have an oxygenated monomer, it can stick to the indium, and it won't react. So the idea here was, what if we have an arm that is labile or hemi-labile and can potentially come off and on during catalysis? And what would be the impact of that ligand system on catalysis? And so Chiral, I'm going to just condense this beautiful study, generated 4 different complexes where he had sulfur, oxygen, nitrogen donors in this arm that can come off and on. And he also had an arene ring as a control experiment where there is no donor. And this is just the structure of one of them. This is the nitrogen containing one. So what he was able to do was he was able to form these dialkyl complexes. So these are dialkyl complexes with an amine, imine, and a phenoxy ligand with this arm that could potentially come off and on. He generated cationic species by just adding a proton source here, so anilinium barf, to this dialkyl compound and generating these cationic complexes. And what he was able to show was that, as expected, the stability of the compounds very much depends on the donor. So when he didn't have a donor, these were very unstable complexes. They would immediately decompose. If we go to a sulfur compound, the stability increased. It still decomposed at high temperatures, but it was stable under inert conditions for about 48 hours. When we went to an oxygen donor, more stable indefinitely under inert conditions. Nitrogen donor, these systems were quite stable indefinitely, and he exposed it to air for days and it was fine. So there really was a tuning of the stability of these complexes with a different donor. What he showed was there was a real difference in reactivity in these systems. So for Chiral, what he showed was that these systems were highly active for epoxide polymerization, explosively so, where the polymer was now all over the glove box, which is not ideal. When the donors were sulfur and oxygen, but when the donor was nitrogen, it was a relatively controlled cationic polymerization of epoxide, and that has to do with donor ability, obviously. And this was also this was observed under neat conditions and under somewhat more dilute conditions. Having the strong donor, the pyridine donor, really changed the stability and the reactivity of these compounds. So a way to think about this is to think about the mechanism potentially. And so if we have a solution, a system where this donor comes off, we know that when systems where the donors are not really good at binding, they decompose. But if we have a situation where we have a system that coordinates but can dissociate somewhat during our reaction, we have enough coordination space available around indium to coordinate our monomers, in this case epoxides, that would lead to cationic polymerization of these systems. And so this idea that to have those hemilabile arms, and specifically the oxygen donors seem to be the kind of in the sweet spot for these systems, allowed us to tune the reactivity of these catalyst systems. The epoxide polymerization is fine, but the thing that Tutura found that I think is really, really interesting is that he was able to show that actually the compounds 2A and 2B, the ones with sulfur and oxygen donors, were not very reactive for lactide polymerization, probably because the lactide would just coordinate to them and sit there. But the nitrogen donor, the pyridyl donor, was actually quite, it was reactive. It wasn't super reactive. This is at 100 degrees, but the conversion was 94%, and we were actually getting really high molecular weights. And the question was, what is going on in these systems? And what Tutura found was that actually he was able to get really high molecular weight polymers with initiation efficiencies that started getting better with reaction time. The dispersities were fine, and it seemed to be a catalytic reaction. But the interesting thing about the system is the polymers are all cyclic polymers. So he was able to get high molecular weight cyclic polymers. These are materials that are really difficult to get. So just for entropic reasons, right, to get the two ends of the polymer to come together at high molecular weights is really, really difficult. And that is what he was getting. And so it was really exciting for us. We were like, what is going on here? I talked to my colleague in chemical engineering to get such high molecular weight cyclic polymers. He was very excited to look at their rheology, etc. And what we think is happening is with the pyridyl system is that arm, that pyridyl arm, is actually behaving as a nucleophile. In this situation, it can actually initiate the polymerization, and once you initiate it, then you have an alkoxide, which is a much better initiator. It can keep on adding monomer until at a certain point, and for a lot of these, it tends to be at the point where they run out of monomer. This alkoxide will then attack this last carbonyl group because it's the most reactive, leading to chain termination, but formation of a cyclic chain. And this is a cyclic chain that is relatively low in dispersity and really high in molecular weight. So this mechanism, the fact that the backbiting in this system is in this very last inserted, or in this case, the first inserted lactide, is the key to these high molecular weight material. We're putting that manuscript together right now, and we're really excited about that ability to control that system. So I have some more time, so I'm just going to talk about this part, this is some work by my student Carlos really quickly. He was able to generate cationic indium complexes. And so the specific structure I wouldn't worry about super much, but they're cationic indium compounds that were able to polymerize epoxides. So here are just a number of different epoxides. And what's important we're including epoxides that can be functionalized. It's really important because we can do post-polymer functionalization, as you'll see. And then he was able to then start looking at the copolymerization of these two epoxides. So we have a chloride or an olefin sidearm with THF. So we can actually copolymerize tetrahydrofuran and these epoxides. He then started looking at 5-membered, 4-membered, and 7-membered rings in terms of oxygen and oxypane copolymerization with epichlorohydrin in this guy here. We can see really high high conversions for both of these, and we're forming these block copolymers in quite a controlled fashion. He was able to copolymerize these with lactide, which is really exciting for us to be able to do that. And what he was able to do is also show that depending on the system, you need to have the epoxide polymerized before you can copolymerize it with the cyclic ethers. They won't polymerize on their own. And again, the key to this chemistry for us was to actually look at the nature of these systems. So in this very first system, what we were getting was random copolymers. We were forming random copolymers of inserted epoxide and other cyclic ethers, and you can see that by the DOSY, you can see that by the DST, where we just get one TM value, and you can see that by the GPC. But what my student Carlos showed was, if you change the nature of the counterion in these, so previously the counterion was hexafluoroantimonate. If you change this into BARF, all we have done now, it changed the nature of the counterion to BARF. And now what we're getting is a block copolymer. And you can see that from the fact that you have two different transitions in the DSC, right? And this has to do with the fact that you have a different mechanism in this case. It has to do with it is a cationic polymerization, right? And so when you're thinking about cationic polymerization reactions, you always have a cationic chain end, I guess, and that the nature of the counterion becomes really, really important in this case. In this case, we have BARF, a really large non-coordinating counterion that allows interaction of this oxonium chain end with the incoming epoxides. And then what Carlos was able to show is that in this situation, once this polymerization is complete, if there's lactide starts polymerizing on this end. So lactide isn't polymerized cationically under these conditions, it's polymerized but via coordination insertion mechanism. So you can have lactide polymerization here while having cationic epoxide polymerization here. That's why you have a block copolymering system. And really quickly, because I know I'm starting to run out of time, I just wanted to tell you this final story, which I think kind of brings the whole thing together. So the idea was, these are cationics, I'm just going to go past the compounds here, but my student June was able to isolate compounds that look like this. Basically, they're indium, cationic indium complexes that have a really bulky counterion and an alkyl. You have seen this motif before, an alkyl TMS methylene alkyl group. And we were excited about the reactivity of these systems. And so they were completely unreactive towards lactide, which is kind of sad, unreactive towards epoxide, under these conditions, somewhat reactive towards caprolactone, but very slow in terms of polymerization. But what they did was, when given an epoxide and a lactone, a 50, 100, 1-to-1 ratio of these monomers, under particular reaction conditions, what we were able to form is 100% conversion to spiral orthoesters. And they're mixture of both enantiomers and diastereomers, but it's 100% conversion. And what this meant to us is that if you think about in the literature the formation of spiral orthoesters, this is a simple reaction where you take an epoxide and a lactone and you get a spiral orthoester. The yields are about 30%. In the literature, people like Matuszewski have shown that you can polymerize them through this mechanism, through a cationic mechanism. And Endo and co-workers in the early 1990s really explored the polymerization of these materials. But if you look at the kinds of polymers they were able to obtain, these polymers, but with very, very low molecular weight, really high dispersities, and it was not a very controlled reaction. So what June was able to do was, instead of doing this reaction with BF3, what happens is it's such a good Lewis acid that it forms the spiral orthoester, but it also polymerizes the epoxide and polymerizes the caprolactone. So one gets a mixture of compounds. What June did was, using his catalyst system, he was able to get 100% conversion, 95% isolated yield of this spiral orthoester. No polymerization of epoxide, no polymerization of caprolactone under these reaction conditions, which is really unheard of. And so this was really exciting for us, because now we can expand, we can start looking at material where we are taking this epoxide and looking at different rings. So we're looking at 7-membered, 6-membered, and 5-membered lactones. We can make these. It doesn't work with nitrogen-containing ones, unfortunately, but we can start playing around with the different functional groups. So if we start with a 7-membered lactone, we can change the epoxide. We can just buy a different epoxide and plug that in there, which was really exciting for us. And if we have a bulky epoxide, we can get a single diastereomer. It has to do with the mechanism. And so this was then expanding now the kinds of material that we can make, which hadn't been done before in the literature. And then what he showed was that if he took these spiral orthoesters that he generated, purified, and he polymerized them with this catalyst at a different temperature, so he made them at 60 degrees. If he took these material at 110 degrees, they polymerized, and they polymerized to form these beautiful, perfectly alternating AB type copolymers. And so the question became, why can't we just have a situation where we can switch on polymerization by making the monomer under these conditions? So at 60 degrees, we're making the monomer. We know that the system goes to 100% conversion. After it's all converted, we can then jack up the temperature to 110 and then look at the polymerization reaction. And that's what he did. He was able to get really high molecular weight polymer under these conditions without having to purify that intermediate monomer, which is really effectively forming an alternating block copolymer of these epoxide and caprolactone under these reaction conditions. I'm not going to go into the mechanism because it's getting late. We can talk about that later if we have to, in terms of polymerization. But one of the things that he's been able to do now is, because he has these side chains, is make cross-link material. And so, for example, if he gets a low molecular weight oligomeric material, and this is probably around 5,000 molecular weight, so it's an oil, it's not really a polymer. You can actually add this cross-linker, and using AIBN radical initiator, actually couple these two And you can see immediately what happens to this material once the AIBN and the crosslinker are added. You get a transparent flexible film. He can change the crosslinker, so you can either have a divalent crosslinker or tetravalent crosslinker, and that changes the material properties. So you can actually get to change the mechanical properties of the material that he's getting. And we're working now with my colleague Savasat Securitas to understand that. So with that, I think I've been given 45 minutes. I'm now 49, so I don't want to overstay my welcome. I just wanted to, with all the, I know that there's a lot of data in this talk, but I wanted to give you an overview of some of the really cool things that we've been able to do with indium systems by changing the ligands, changing the electronics of the system by making them into cations. And we've been able to really polymerize still a relatively narrow, I would say, list of monomers, but these are expanding. And so we can look at lactides, epoxides, lactones, acrylates. We can look at copolymers of these material and really control these. We can start looking at spiral orthoesters, really expanding the functionality of these material. And so we are now just starting to really, we can make these functional material, but then what? Right? The question becomes, then what can we do with them? What can be done with them? And so this is where we're collaborating with colleagues in pharmaceutical sciences, in materials engineering, to really take advantage of the platform technology that we've generated in being able to make kind of a Lego bag full of different kinds of polymers and start looking at their applications. The other thing that I wanted to highlight is this idea that indium complexes can be tuned. They can be tuned by ligands that are around them, by their denticity, by very subtle changes in electronics in these systems. And one of the keys to the reactivity of indium complexes is to be able to control aggregation in these systems. And if you can do that, it can be really amazing options in catalysis. So with that, it only remains for me to thank my fantastic group of students, completely resilient. It's amazing the way that they have been able to deal with a very difficult situation and really thrive. And I want to thank them. And specifically in this talk, I spoke about the work of Carlos, June, Chitura, Dinesh, Steve a little bit, Tanaz, and Inson Yu, who are these students that have really worked on the different parts of this. My collaborators are listed here. Specifically, I talked about the work that I've done with Savasat Securitas. I've had support from a number of different sources, but most importantly, I want to thank NSERC, which is the Natural Science and Engineering Research Council of Canada, which has supported me in a lot of different varieties. So with that, thank you again for this wonderful invitation. It's such a pleasure to be able to tell you about my work, and I would be very happy to take some questions.
Thank you so much. Hello, Professor Parisa. Professor
Yes.
Mehrkhodavandi, that's fantastic. Thank you so much. You have done a wonderful, excellent, very informative lecture, and it's filled with, very rich indium chemistry. It's amazing to see how indium can be used as a catalyst to ring opening reactions to make biodegradable polymers with ester links. Fantastic chemistry. And now it's time for us to entertain questions. And this session will be handled and moderated by Dr. Lahiru Vijayanayak. He's the Vice President of the SLAAS Section E2. Okay, over to you, Lahiru.
Okay, thank you, madam. Can you hear me?
Yes, I can hear you.
Okay. So let's get started with the Q&A session. Thank you very much, Professor Parisa, for that very nice and enlightening talk about all the beautiful work that you have been doing. And I'm sure it's very late for you already, but if you can please bear with us a few minutes, I'm sure there are plenty of questions that the audience may have. So we are about to start the Q&A session. A couple of reminders. You may post your questions in the chat option, or you may also unmute yourself and ask questions if you have any questions. And I will ask the questions, and I'll prompt for your name if you can post your questions in the chat option. We do not have any questions in the chat option right now, but if you do have any questions, please go ahead and ask. Yes, madam.
Yes, Lairo, I have. Yes. Professor Parisa, how stable are these complexes, especially this cationic indium complex?
So this is really interesting. The cationic indium complexes, we can tune their stability. So depending on the donor group, so for example, Chitura's work showed that depending on the donor group that we have, if we have a really strong donor like a pyridine, they can be completely air stable in the solid state. But
really?
if you don't have a good donor, so if you have, for example, a sulfur donor or no donor, they can decompose in the glove box within minutes. So it depends on the donor group, and it's really key to these.
Okay, and also when you are synthesizing these indium complexes, you use very inert conditions in the glove box. So how do you manage this?
Well, so because I'm an organometallic chemist, and I'm used to, this is kind of how I'm used to doing this chemistry. Just as a matter of form, we do use kind of air stable, air sensitive, glove box, nitrogen environment. But on occasions where we have systems that accidentally get exposed to air, and we realize how completely stable these complexes are. So we do treat them with under inert conditions, except when we are really trying to show how stable they are. So for example, I showed you this one example of the compound that was completely air stable. It's completely air stable, and you can use it under air. So not all of them, but there are some of them, depending on if you're choosing the right ligand, they can be quite stable.
Okay, thank you very much, Professor Parisa, for that explanation. Professor
Lairo, can I ask a question?
Yes, Professor Nalin, please go ahead, sir.
Thank you, Parisa, for the fantastic presentation.
Thank you.
I'm Professor Nalin, presently the head of the department.
Yes, fantastic. And also, Indian tin oxide is supposed to be, thermal sensitive with IR light or yes. Okay, you go ahead. I'm sorry to interrupt.
Okay. It was a nice talk, and my question is, Parisa, you use the known biodegradable polymers, but when you make a new polymer, how do you test the biodegradability? I know it's a tedious process. Can you just explain whether you have done any biodegradable work on these polymers?
Yes. So this is a very good question, and it's a very important question. When somebody says my material is biodegradable, the question should be, is it? And so the answer to this is, depending on the polymer, not all of them we have, but the ones that we have, we're actually collaborating with a colleague in UBC Okanagan. She's actually in the biological and chemical engineering department there, and she actually takes material and looks at their degradability studies, specifically, using laboratory methods. She actually takes them to landfills and look at their degradation. The problem with this is that when you're making material, that the scale that we're making them maybe on a 2-gram scale. And for us to do a real degradability study, we need to actually make quite a bit more material. And this becomes a little bit tedious for us. So if we want, we have done degradability studies on a larger scale on 2 of our polymers, and they have shown various degrees of degradability, but we haven't done it for all of them. And it's important to say that that we haven't. The only thing that I can say is that we have done polymer molecular weight decrease studies, where you can actually see the molecular weights decrease over time. That's not enough though. So to actually say something is degradable, you have to actually follow a certain standard. And that's hard to do because you have to make a lot more polymer than we can. But we can actually watch their molecular weight go down with time. It's just not enough. Sorry, I hope that answered your question.
Yeah, I think I expected that answer, because you know the measuring the biodegradability is not a easy process, and there are I think the other methods that you can speed up the biodegradability ability of a polymer. I think those instruments are available probably perhaps in material science.
Well, so it depends. There are different ways. For example, I've worked with polyolefin companies where you can actually put in photoactive material inside the polyolefin to get it to degrade. It's just under what conditions are we talking about? What's interesting though is about a lot of these biodegradable polymers, they actually have stabilizers added to them to prevent them from degrading. It's really interesting. Because if you make, for example, polylactic acid is the kind of the most common one. Polylactic acid that you buy actually has stabilizers added to it to prevent it from degrading, because the stuff we make in lab actually degrades much faster. So it's an interesting point I never thought about, but actually a lot of the degradable material that we get actually is being prevented from degrading because it needs to be shelf stable. So if you buy something that is in a PLA container, you don't want it to degrade immediately. You want it to slow down from degrading. So it's a much bigger problem, which is why my answer to this is we should very much reduce the use of single-use plastics for a lot of different applications. Plastics companies don't like me when I say that, but anyway, I say it anyway.
I know that. Yeah. Thank you very much for your comprehensive answer for that. This is just a comment that as the head of the department chemistry, very happy to see two of our best students worked with you, Dinesh Aludge and Chatura Gunasinghe, and hope that you will hire more students in the future. Yeah, from the chemistry.
I'm looking forward to it. Send me those applications.
Yeah, thank you. So over to you, Lahiru.
Thank you, sir. Thank you very much, Professor Nalin, and thank you very much, Professor Parisa, once again for that very interesting explanation. That perfectly makes sense, madam. And one more question actually that I had was you explained about the indium taking part in the preferably chain termination reactions versus the chain propagation reactions.
Mm-hmm.
Can you kindly elaborate on why that happens? Preferably, why does indium lead to the chain termination over the chain propagation reactions, madam?
I think a lot of the story that I hope to share with you is the fact that it is the reactivity of these systems is highly tunable with the ligand that's around it, right? So if you have a ligand system around these indium catalysts that will preferably form the dimers in the very beginning, if you remember what I was talking about. So if you form those, so let me see if I can share my screen with you really quickly. It's easier to show you. So if we have a hold on. So if we have a system here, where is this? Can I share screen? Yeah. If I have a catalyst system that allows me to form these dimers, the chain end is going to be basically trapped between the two indium centers. And it's the chain end that can go around and attack another carbonyl in the chain, right? This is what is doing, this is the active part of the polymer chain. This is what is going to go and attack another carbonyl group. If we have two metal centers in this case, it's going to be basically taking that chain end and deactivating it. So the only thing that this chain end is going to react with is another lactide that's right next to it. It's not going to be able to go around and react with the rest of the chain. I showed you later, much later in the talk, so over here, when we were looking at the cyclic species, where now I'm forcing it to be monomeric, right? This is now forcibly monomeric system. And at this point, that chain end is bound to one metal. And this is where it's going to be able to attack, because there aren't two metals that are binding it. Does that make sense?
Yes, Professor Parisa, that makes perfect sense. That was exactly the answer that I was looking for. Thank you very much, Professor Parisa. And I do have a comment to make, actually. As a scientist, I really like how you phrased the statement about the use of plastics, because of course we cannot, at this point of time, we cannot avoid the use of plastics. Rather, what we should do is to identify where it should be used and where we could minimize the use of plastics. So that makes perfect sense, and that's basically what we should be doing in terms of a sustainability perspective. And in an overall sense, Professor Parisa, I would like to ask, as a scientist, what is your overall opinion on the use of plastics in the different applications in view of sustainability going forward?
Well, I mean, I think it's very different in different parts of the world. So I was in Bali, and when you're walking around on the beaches of Indonesia, you see how, I don't know, the word to use is desecrating. There's something kind of desecrating about the way that you see these plastic bottles everywhere. And it's just, I don't know, there's something, Bali is a very Hindu island, right? And you kind of get very, I'm not Hindu, but I felt there's spirituality there that's marred by this plastic. I know it sounds kind of mushy, but there are a lot of applications where it's not necessary. This is not a necessary fact. You don't need to have a Starbucks coffee cup, which is it's a very Vancouver problem. We can't, if we don't have coffee, we can't survive. It's so rainy here. That it is everywhere. You see these everywhere, and it's such a not necessary thing. So even at the height of the pandemic, if they had a situation where you could take your own mug and they wouldn't handle it, they just poured the coffee in there without touching you. If there is a will, there's a way. And so the idea has to be that how can we as a society avoid using these single-use material, because we can. There are definitely ways to do this. And if we priced the price that we pay for that pollution into the plastic, it wouldn't be so cheap anymore. Starbucks couldn't afford to give away so many plastic cups anymore because it would be too expensive. And I think that it's the same as pricing carbon, CO2 pollution, right? And it's mostly the rich countries that are just completely not thinking about this usage of this material, and it is so wasteful. And I think there needs to be a real societal change in how we approach just technology, not just plastics, but technology in general. Don't throw out the baby with the bathwater. We need plastics. We need this material. It's just, what are the applications where we should be using them, and what are applications where we shouldn't be using them?
Thank you, madam. That makes perfect sense. And actually, like you just explained, madam, it's more of a global concern right now. So we need a change of the mindset. So it's all about the attitudes, and we need to adopt the proper practices globally, and we need to have a set of standards, and that will definitely minimize the crisis. So thank you very much for your time, Professor Parisa. Are there any other questions from the audience? Well, it seems that there are no other questions. So thank you very much, Professor Parisa, for that wonderful presentation. It was very interesting to see the beautiful work that's carried out in your research group. So that's the end of the Q&A session.
So I look forward to hopefully being there in person and seeing your wonderful country in person. It's a dream of mine, and I'm looking forward to it. Hopefully, when everything is back to normal. So
definitely. Hopefully, fingers crossed. We are all hoping for this pandemic to go away as soon as possible. So most of these virtual meetings will be held in person, Professor Parisa. So hopefully, we'll get to meet you in person someday soon here in Sri Lanka itself. So on that note, thank you very much, Professor Parisa. And I would like to now hand over the controls back to Professor Rohini.
Yes.
Over to you, Professor Rohini. Thank you very much.
Thank you, Lahiru. Thank you, Lairu, for coordinating the session, and also, as Lairu said, Professor Parisa. I think, hello, yes, it's very nice, and thanks again. And I also would like to thank my student. He was my former undergraduate research student, Chatura Gunasinghe, for introducing me to you. Wonderful to have you. And
same, it's the same.
As Lahiru says, we will hope to see you in person in Sri Lanka one day. Soon.
Looking forward to it.
And it's now time to give a formal thank you note by Dr. Gayatri, Secretary from the SLAAS E2. Thank you so much.
Thank you.
Okay, Gayatri.
Yes, madam. Can you hear me?
Yes.
Perfect. So, hello everyone. So we are at the end of today's webinar, and I'm sure all of you have learned a great deal about the power of catalysis to address environmental challenges. So on behalf of SLAAS E2 2021 team, I would like to thank Professor Parisa Mehrkhodavandi for taking time from your busy schedule and accepting our invitation to share your expertise on new catalyst design strategies for polymerization reactions. And we wish you all the very best to drive your research to the next dimension in this new year, to successfully address the global challenges, especially the pollution problems, with your timely innovations. So thanks again for honoring us with your presence. And I would also like to extend my gratitude to Mr. Chatura Gunasinghe for arranging this fantastic talk with Professor Parisa. So, and I'm also thankful to the students, academics, and researchers for your participation, response, and cooperation to this event. Thank you for such productive discussions, and thank you very much for joining with us. And last but not least, I would also like to extend my gratitude to all the people who were directly and indirectly helped me to make this event successful. And also, all these webinars organized by SLAAS E2 will be available on SLAAS YouTube channel. So please visit www.slaas.lk for more information. And Professor Rohini, I think we can wind up today.
Okay, thank you, Professor Parisa. Thank you so
Thank
much.
you, everyone.
Yeah, be
Thank
safe.
See you.
Bye-bye.
Bye.
Bye.
Thank you. Bye-bye.